So thanks for the invitation. Yeah, I want to talk about the opportunities and the challenges for laser technologies in e-mobility applications. Especially, I want to give some hints and yeah, some things we have to keep in mind to consider if we're thinking about laser technology for e-mobility, especially for high mass production. So the motivation is quite obvious. The motivation for laser-based manufacturing is mainly driven by the trends and the global demand for sustainable mobility. Yeah, this is rising and rising, and we as Bosch, we for sure we focus on these demands. We spent in 2022 above 800 million euros in electrified mobility in some production lines. And therefore, we now reached up over 5 million vehicles with Bosch powertrain components. For us, it's quite important to have a sustainable, have some sustainable solutions. So, for example, we want to increase the range for you all. We want to have a sustainable production. We also focus on the infrastructure. And for sure, on the cost itself, we want to have all the parts and the things afterwards very cheap, that we all can buy it, and this all with a worldwide CO2 neutral production since 2020. This is yeah quite important for us, and with this motivation, we develop components as well as products for the entire mobility sector, as you can see here on the left-hand side. So starting from the e-bikes to scooters for the passenger cars and trucks and so on. So we have the whole entire mobility sector with our products and components. And on the other hand, our products and technology are represented in the complete and the whole integration level and the whole vehicle classes. So starting with very thin and small parts with the semiconductors, over the subcomponents like power modules or stators, rotors, to components, the whole engine, the e-drive, and we end up in complete integrated solutions for our customers in combination with energy storage and conversion, like the batteries and fuel cells. And I think you all know that if we want to have such innovative products and if we want to develop and produce them, we have to have innovative technologies for a flexible and robust and cost-efficient production. This is very, very important, and we think that the laser is one of the key factors and one of the key tools to do so and to gain this this productivity and the cost-efficient productivity. So we have the very innovative products, for example, the batteries, the fuel cells, which increases in complexity and which increases in functionality, the power electronics and e-drives, and we have to need the suitable tool for producing them. The laser is one good tool. I think you all noticed the laser is the enabler technology for new product features, for innovative products. It's very high productive technology. It's flexible, automotive, and has a very low energy consumption. So overall, the laser is very cost efficient. So why not use this for mass production? And there are some challenges to handle. And this challenge can be easily explained just by a few simple calculations for which I want to take you to small deep dives. So if we just take a look at the changeover from the conventional powertrain to the e-powertrain, so from more like steel parts to copper parts, not all copper parts, but in most of the cases. And if we just have a look to the requirements on, for example, the welds, and then we have, for example, we came from the thickness of the parts from the conventional powertrain, we came from 300 microns to roughly about 1 millimeter in thickness. This was always for injection pumps or for Bosch products, for high pressure pumps. And now we end up with a very, very increased range of requirements for the thickness where we have to fulfill. So we are from 10 microns for the battery foils, for example, and we end up, in this case, for copper, to weld copper 5 millimeter thickness, which is really challenging using the lasers. So, for example, for busbar welding for e-drives. And this increased requirements, this increased complexity will be much more pronounced if we have a look at the welds per part. So if we came from 1 to 20 welds per part, for example, for the high pressure pumps, then we end now in 1 to about 8 or 600 welds per part. And these welds are all responsible for the functionality of the product. And if one weld is missing, if just one weld is missing or has a failure, the whole part can be destroyed. And this is quite important to know, that we cannot throw the parts away because they are also extremely expensive nowadays. So we have to consider that this complexity of these new products, of these new materials, are extremely growing, and we do have to think about new strategies, new system technologies like the laser technology for a robust welding process. Otherwise, we have not a cost-efficient production. And just another simple calculation to show you how important it is to know the process, to know the process chain, and to consider all the things around the laser is done with a rough estimation by producing fuel cells, for example, the bipolar plates. And if we just calculate the production of some bipolar plates, so we have, for example, 150 to 250 millimeters in square of the bipolar plates, then we end up with a sealing length, so a welding length, if we're using the laser, for 1.2 meter. And if we assume that such one bipolar plate has an output power of roughly 320 watts per bipolar plate, and we want to end up with, for example, 100 kilowatts fuel cell stack, then we have to weld 384 meters in laser welds, and all the laser lengths should be reliable and for sure tight over lifetime for the fuel cell stack. And if you go a step further, if we assume we want to have 1 million cars per year, for example, with 1.4 percentage of cars which have a fuel cell inside, then we have to have a weld a length of 384,000 kilometers a year. And this is exactly the distance from the Earth to the Moon. So I think these numbers show quite easy that we have to know about our process. We have to know about our tool, our laser in this case. If you imagine that we're using a 50 micron focal diameter, for example, 100 micron, and have to weld defect-free about 300,000 kilometers a year, this is quite challenging. And this we have to keep in mind. And another example is if we weld copper. Copper is quite challenging at laser welding, and we do have to weld copper if we're talking about production of e-drive. So production of hairpins, for example, or stator. We have this light blue requirements here. We have spatter formation, we have melt ejection pores if you do not use the right parameters. We have a high heat input, we have a variation in penetration depth. And what we do have too is we have to consider the whole process chain. So the requirements from the process chain, so the product geometry, the environment, accumulation of some defects, tolerances, and so on. So it's not anymore only developing the weld itself. So we have to consider the whole process chain. So it's not sufficient to take only the weld into account. So we have to take into account that we have relevance in influencing factors, effects. We have to understood the whole process. And we have to understood the influencing factors and the physics behind the cause-effect relations. Then we gain and end up with a high efficient production. Also, one easy example is if you want to weld such stator production for e-drive, there is not only 1 or 2 or 100 welds where you have in the lab with totally perfect condition. In production, at the very first beginning, you have this perfect condition, but for a production line which runs over several years, you have some issues, for example, with the process chain, with contamination from parts you will buy from suppliers, from the process chain itself. In this case, there's a quite easy example. If you have the stripping process from e-drives, if the stripping process for copper wires in before of the weld, and just one simple wire has a pure stripping qualities or acetyl layer from this isolation is still on your wire, and you want to weld this, then you end up with this high-speed image which you can see here. So you end up with a really huge pore formation, which you cannot see after welds, which you cannot see with visible inspection. So you have to know about the process. You have to consider the process chain. You have to consider the interaction between some contamination, some other effects for a stable welding process. So it's not enough to look at the lab. You have to also take into account the whole process chain. And therefore, you have to know and have to have a deep understanding and have to know the influencing factors of the whole process chain. And this will become very important for mass production, especially for the e-mobility selection. So just want to show you some examples that we have to face on if you do mass production. And just a short summary, I think there is a global demand for sustainable mobility, and this is rising and rising. And we, as Bosch, we offer innovative products and technologies where we face on this complex, this complex process chains, these complex processes. And I personally, and we think that the laser technology is one key factor for today and future's electrified mobility. There is no single fuel cell, no single battery, no power electronics, no e-drive without even one laser technology. So we need the laser to be very fast, to be good, to be sustainable. But therefore, we have to know about the process fundamentals. We have to know about deep technologically basics, the basic understanding, and then we have to transfer this. This is quite challenging, but I think we are on a good way. There is still a great demand for novel laser technology, is still arising. We have innovative solutions. So I think together, laser technology has a great potential, and we can make the future, the future with sustainable mobility if we transfer this technology USP from the laser to real products. Well, thank you. Hopefully, I can give you a short overview of the challenges in e-mobility. Thanks.